Good morning, everybody. Welcome to this course on AMD GPU programming with HIP. We're on the sixth day, the last day of this 6 day course, and we were talking about synchronization yesterday. We'll finish up synchronization, try to finish up synchronization quickly today and move on to some rather important topics in HIP. So I'll just start with a brief recap of what we saw yesterday. And then there were a few doubts yesterday which was not cleared, so I'll clear those after my recap. And then we'll start with exploring global barriers, implementing global barriers once again. So we saw what was synchronization and why we needed it. And then we saw what a data race is and some basic concepts of uh, synchronization like data race or deadlock or starvation. And we saw when a data race can occur, like when multiple threads are involved, and both of them try to update the same memory location. We saw that one instruction can be broken down into multiple smaller instructions like load, update, and store, and this can be interleaved on these can be interleaved, and this causes data inconsistency. And when we saw a sequence of operations which could cause such a inconsistent result. And then we saw what was the how we could overcome a data race, which was to make operations atomic, such that these individual operations, load, store, and update, happens as a single instruction rather than multiple instructions. Then we saw what deadlock was and what starvation is, and uh, yeah, what atomic operations were. Uh, then we moved on to mutual exclusion, where mutual exclusion refers to the property that ensures that multiple threads do not simultaneously execute a certain sequence of instructions. And these sequence of instructions which should not be executed simultaneously are called critical sections, and they usually access some kind of a shared resource like memory location or something, and it is crucial for maintaining data consistency. So we would have learned the logs, semaphores, and monitors and constructs like that in operating systems. And we saw how to implement a rather simple mutual exclusion construct for two threads. But this won't be a general case. It's rather a very simple construct which we came up with so that we can understand mutual exclusion a little better. And we saw what a volatile variable is. And we tried to implement lock in and lock functions for in two thread scenario, and we saw that we could implement lock in and lock function like this. But this had majorly two problems. One is that mutual exclusion was guaranteed, but deadlock was possible, and starvation is also possible in this case. Now, then we moved on to another situation where we could prevent the deadlock, but even so, starvation was still possible. So, both the solutions which we saw so far had some kind of a problem. Uh, so, what we did is we combined both the ideas from the previous two solutions, and then we saw a solution called as Peterson's lock, which guaranteed mutual exclusion, and starvation and deadlock was not possible in Peterson's lock. And then we moved on to the bakery algorithm, which was a more it was for n threads rather than two threads. And I made a small modification in the code here, which is that yesterday was supposed to be while for all k there exists a k, and I've implemented it as a for loop so that there is no confusion there. And then we saw why locks are prohibited because and how we can that we learned that we can use atomics to implement locks on GPUs as well. Then we moved on to atomics, which again are primitive operations, like whose effects are fully or visible only fully or not. They'll never be partially visible to any thread. And it requires hardware support, and it works with both global, local, and shared memory. And then we saw that there is a problem, like there is a mistake I made in yesterday's lecture, so I'll explain that once the recap is over. And we saw how to fix the SSP case here. And then we saw what atomic gas is. Atomic gas is a compare and swap operation which happens atomically. So it compares. We're given we given a memory location, so it has an old value, and then we want it to be updated with a new value. So what we do, and we are given a comparison value. So we check if the old value is the same as a comparison value, and if it is, then we update it with the new value, or else we update the address with. Well, we don't change the old value, and all this happens in a single instruction. And so this gas can be used to implement locks, and also atomic gas can be used to implement other atomic functions. There was another doubt yesterday regarding atomic multiplication, and I'll come to that as well. Then we have other atomic operations like atomic maximum, atomic add sub, and then there are a bunch of other atomic functions, atomic increment, decrement, and or XOR, and exchange is also there. And we wanted to see how to implement a lock using atomic gas. We saw different variants of this atomic gas, and why uh, some of them will not work. In this case, there's no waiting at the intersection. Like if one thread fails to do atomic gas, it just exits the. It just continues into the critical section anyway. So there's no waiting, or mutual exclusion is also not guaranteed here. So even if in this case, what happens is we've moved the critical section inside an if block. In this case, threads will not even try to enter the critical section if they don't. They are not able to do CAS properly. And now we have another case where we have this will almost work, but the problem is that it works across wave across work blocks, across wavefronts. But within a wavefront, this will fail because there will be a like the wavefront threads will not be able to execute in SIMD fashion, because the one which acquires the old value as 0 will exit, whereas the other threads which do not acquire old as 1 will go back into the do while loop. So this will cause the threads to hang. So what we did to we made a small minor change to this so that we can fix this issue. This is that we had added we used the thread masking feature of wavefront threads to make sure that we are still in the while loop, but we continue this keeping doing this check, so that threads do not have this problem of separate, let's say, flows. Then we saw something called as barriers. So barrier is essentially where it's a point where all the threads will wait till the rest of the threads. It'll stay at that point till all the threads reach that point. So we saw different kinds of kernels of, barriers so far, which was that one was sync threads within a wave bar group, where we had where we waited for all the threads in a wavefront in our group to reach that point before we proceeded further. Then we had HIP device synchronize was another barrier between host and device. Then we had the so end of the kernel acts, end of any kernel will act as a implicit barrier for GPU threads, which means that all the threads will wait at the end of a kernel if there are other, and only then proceed to the next instruction in the GPU queue. Uh, yeah, and within a wavefront, we do not need synchronization because they'll all be executing in SIMD fashion anyway. And then we saw how to use global barriers, which is used to synchronize across work groups. So one way to do this, and how we used to do it earlier, was to split the kernel. Like assume we had uh, 4 lines of code, 10 lines of code, and after 5 lines, like in the original kernel, we had 10 lines of instructions, and after the fifth instruction, we wanted all the threads to complete their execution at that point. So what we used to do earlier was that we used to split this original kernel into two kernels. The first kernel will do the first 5 lines, and then the second kernel will do the second 5 lines. And we used to schedule them one after the other so that there is an implicit barrier between them, which is the end of the kernel barrier. But then they came up with grid.sync, which was cooperative groups, which could essentially make sure that the synchronization, the barrier, we don't need to split the kernel to get the barrier. So this was better because there was no kernel launch overhead. We could overcome that issue of launch overhead. And then this is where we stopped yesterday, which is that we tried to implement a global barrier using atomics. So I'll explain this. Before that, so there were a few questions yesterday as to one question was, how was starvation possible when we had that victim case. So so the sequence of operations that can possibly lead to a starvation here is that let's say we have two threads, T0 and T1, and so what happens is T0 sets itself as victim is equal to my ID, and then it goes just before going into the while loop. T1 comes and sets victim, and then goes into the while loop. So right now T0 is just before the while loop, and T1 has set itself as the victim and then went into the while loop. So now T1 is waiting inside the while loop. Now what happens is T0 resumes, and it sees that the victim is T1. So which means that it doesn't have to wait in the while loop. So it goes into the critical section, and then proceed. It does the operations. It unlocks, and then it immediately tries to reacquire the lock before T1 exits the while loop. So T1 is still in the while loop, maybe in a preempted, like it's not executing, but T1 finished, T0 finished its execution, went back, and then tried to acquire. I tried to acquire the lock again, and in this case, T1 is still waiting. So it immediately it's possible to reacquire the lock. So this is a case where starvation is possible. And then there was a question about atomics with wavefronts, which was asked by Viren. That is in that case, it is actually there's some confusion with respect to that. Which is that I had made a mistake saying that they'll all be executed atomically, even if it is we don't use atomics. But Viren had pointed out that because they are executing in SIMD fashion, only one update will happen. So I tried running this code, and it so happens that the update will happen only once. So if 64 threads are trying to update the same, increment the same variable, which was initialized to 0, the output I observed was 1. But then, like I spoke to my prof, and like I searched for a few online resources. What happened is that what they said is that it is not always possible that it will be 1, but it is definitely possible that it won't be 64. I mean, the chances are very less that it's 64, because there is a chance that that there can be some inconsistency in the output. So how this happens is like not clear to us, or I couldn't get an answer to why it is possible that we'll get a non-one answer. But theoretically, it is true that the only update should be the increment should only happen once, because the like sub instructions which give the instructions of that increment operation, like the load, store, and update operations, should happen at the same time for each of the wavefront threads. But from what I've heard from like my prof, who said that it is unless we use atomic, we'll not be able to guarantee that it reaches 64. By the same time, we can't say that it's one either. But like I think I tried running that code over and over again, but even in that case, I couldn't come up with an answer which was one. So theoretically, it is one, but from what I've heard and read, it looks like we can't guarantee that it will be one all the time either, because of uh, hardware and stuff like that. But not exactly sure. But my observation is that it was only one. So if we use atomic, yeah, then we'll actually see 64. That is definitely the case. That I tried out, and I actually got a 64, and it was confirmed that we'll definitely get 64 in such a case. Actually, I will just try running that code once, just to make sure if that is the case once again. And then there was a question about the atomics data type. What are data types are supported by atomics? So in HIP, the three things that I could see was int is supported, and then unsigned int, and then unsigned long int. These are the three data types which are supported for atomic gas. But for other functions, it may vary. So we'll have to check the documentation before using a specific data type. But always there is this case that we can, when we compile it, if it's not supported, we'll get a compiler error saying that it's a like the conversion is not right, or something like that. And then there was a question about atomic multiplication and division. So regarding this, there's no pre-built, or there's no function which exists regarding multiplication and division. But one thing that we can do is uh, create a lock using atomic gas, and then do the multiplication operation within this lock, so that the multiplication part happens as the critical section of the lock. Section after the lock. So this will make sure that the updates, the multiplication is guaranteed to be atomic in nature. But other than that, there is no existing API which gives atomic multiplication or division. And then there was another question about locking the array and locking the element of an array. So we did learn what are locks, and then we have after the locks we'll have a critical section, which usually accesses a common data element. So what locking a whole array means, that only one thread will be able to access any element in that whole whole array. So which means that only one thread will be accessing any element in that array. And then when it comes to locking an element, the thing is that one element in that array will only be accessed by one thread. Which means that multiple elements will be working on multiple threads will be updating multiple elements, but no two threads will be updating a single element of that array. So that was with it about it with the doubts that we got yesterday. So there was this mistake regarding wavefronts, which I'll also put in the group in case if anybody missed it, so that we can clear that issue. So we'll move on to the global barriers implementation. I'll just explain it once again, and we'll move on to the next section. So again, we maintain two integers, global counter and global flag, and we use this sync method to synchronize across blocks. So sync will be called with the number of blocks that we launched the kernel with. and then we take a representative thread from each block, which is thread id x.x equal to 0, and then we increment the counter value for each block that we see, and then we check if we've seen the last block. If it is the last block, then what we do is we reset the counter, and then we negate the value of negate the value of the global flag. So all threads from each block will wait at sync threads, and once a block from each block, I mean, or from when all the threads reach the first sync threads, it'll go into the while loop and then busy wait there, because global flag is only one when all the threads from all the blocks have reset, because we are checking if if it's the last block, and the last block is what does the atomic exchange, and then sets the global flag as one. So that when we reach that while loop, the second while loop, the only while loop, which is the busy waiting while loop, it would mean that when that breaks, it means that we've already seen all the threads in the block. So essentially, that means that all the threads of all the blocks will wait at this busy waiting while loop um, till all the blocks have reset. So this whole synchronization construct can be used as a global barrier, and it can be used multiple times. Like even if we use synchronizations in a row. So, there was an example where we could not use synchron. We can come up with a solution where sync cannot be used twice in a row. Like if we use sync once, we'll not be able to use it again. So that is not the case here. Like because of the lack of time, I didn't add that example. But yeah, that is one possibility. So you have to be sure that if at all you have to implement global barriers, you have to be careful of a few things. And then we'll move on to what is called as data and control synchronization. So control synchronization, essentially, we've seen different types of control synchronization, like sync threads, grid.sync, even kernel exit end of a kernel. These are control synchronization. So what they do is they ensure the order of execution of threads, or it usually deals with the coordination between threads. So just a moment. So what control synchronization does is, like I said, the order in which they are executed, all this will be taken care by control synchronization. And then we have something called as data synchronization, which is data synchronization essentially ensures that there is consistency amongst the various threads for data reads and data writes. So if one thread updates a certain variable, it might not be immediately visible to another thread. So data synchronization constructs will make sure that that update will be visible to other threads as well. So when it comes to control synchronization mechanisms like sync threads and grid.sync will definitely ensure that we have data synchronization. So control synchronization essentially will also take care of data. So if we have a sync threads at a point, and then we have let's say a global memory location. So when one thread in a block updates that global memory location, and then we hit the sync threads, this would definitely mean that the other thread will also see this update made by the other thread. So for explicitly doing a data synchronization, we can use there are two constructs called as underscore thread friends and underscore thread friends underscore block. So essentially, thread friends will be used for all the threads within the GPU. So across work groups, we can use it. So when let's say somebody updates a specific a global memory location, and so as it encounters the thread fence, it will definitely any reads or writes after this thread fence will be from the updated value in the global memory. And thread fence underscore block is used within a thread block or a work group. And so essentially they make sure that the write made by a thread is visible to other threads as well. So any read after this will also be the updated value. And yeah. So this was the for loop case, which the for loop, when we parallelized the for loop in the initial lectures, where we launched 1,000 threads, each with yeah, 1,000 threads, and each of them was printing the square of the thread ID. So what we saw there was that even though it printed the correct output, we had a problem that it was coming out of order. So this is one solution that we can come up with, where we just make sure that there is a busy waiting happening, where we where we where we have a busy waiting case, and we check the thread ID. If the thread ID is not equal to counter, then we busy wait, and if it is counter, we proceed print and then atomically add the counter. But again, there is the same problem that we saw with one of the lock implementations. So, which is that warp threads will have a problem here. You guys can do one thing, which is that you can try. This is a homework how to fix this kernel. So the idea is just to use logs, and you may have to think a little outside the box, and you may not get the result at the first go, but it is pretty straightforward when it comes to, like, once you figure out the idea, I think it'll be pretty straightforward. So these were the different synchronization primitives which we saw, which was that sync threads, and then we saw atomic operations, and thread fence, block thread fence, and then grid.sync. So this is a kind of a comparison as to what is the scope of the control sync and data sync. So within a thread block, control sync will happen. Control sync will happen only within the block, whereas for a data sync, that will also happen within the block. And atomics, there is no control synchronization as such, but data synchronization happens across all the globally. But for a shared memory variable or a local data store variable, it will be within the block, because of course that data item will not be accessible outside the work group. And then thread fence block data synchronization scope will be within the block, and thread fence will be across all the threads. And finally, we have grid.sync, which gives control synchronization and data synchronization across all the threads in the GPU. So we'll move on to something called as reductions and prefix sum. So this is a application, kind of an application of logs and barriers and things that we've learned so far. Prefix sum is kind of a reduction. I'll be taking this a little bit quickly, right? I won't be asking a lot of questions, but yeah. So reductions essentially are, it usually deals with converting a set of values to a very few number of values. Let's say we have to find the sum of n elements. This is a computation which is reducible. So when we say that the computation must be reducible, it means that that computation should essentially satisfy the associative property, which is that if there is an operation, let's say dot is associative if we have a dot b dot c, which will give the same result if we do a dot b first and then dot c, and then we do a dot and then b dot c first and then do a dot the result of b dot c, we should get the same output. So these are the operations which computations which satisfy the associative property. So if you see the addition operation, we can see that it is associative in nature, or max operation, finding the maximum of some elements of 3 elements, that is also associative in nature. And this is usually implemented using atomics. And so reductions can be used to improve parallelism. So this is an example of how we do, how we can find the sum of like say 8 elements. So at each iteration, we so there will be login steps, and each iteration will do yeah, find the sum of 2 elements each, and then so in the second iteration we'll have two sums, and the final iteration will have one sum. So this is like say sum using reductions. So this will be more beneficial. So, but if we implement this on, let's say, on the CPU, this will anyway take n operations, which is as good as doing it serially. But when it comes to doing it in parallel, it'll be it'll also be, I think, n additions will be required, but the we can exploit more parallelism because we can do let's say 4 and 8 addition at the same time as 3 and 9 and 1 and 7 and 5 and 2. And in the next step, we'll need the sum of these two and then these two. So, yeah, does anybody see like we require barriers here? Where do you think we'll be requiring barriers? You guys can take like 1 minute and tell me where all we'll be needing barriers in this kind of a computation. Viren, that's a good question. Yeah, we'll assume that it's stored in the original array rather than a new output array. But I guess even if it is a different array, we will be requiring barriers. Yeah, that is correct, Viren. So yeah, we'll need a barrier after each of these steps that you see. Uh, Only once all the sum of all this is completed, we move on. We should move on to this, and then to this, and then to this. So obviously, this is in an eight. If you only have eight elements, then it won't be a problem. Mainly because we have well SIMD operations, but when we are dealing with much bigger arrays, we have this problem. So this is the implementation of reduction using yeah, reduction for sum. We also need a single each sum. So yeah, that is also correct, Viren. We'll need because garbage value, yeah, the old value will not be right. I'm not sure why there would be garbage value if we are using the same. If it's a new array, yeah, that's correct. If in case of a new array, we'll be dealing with garbage value or the wrongly initialized value, whichever it was. So yeah, this is a simple reduction code using for sum. So what happens is what we're trying to do is we'll store the. If you can see, we don't need exactly the uh, an atomic operation here. So this kind of the implementation here will be adding up. Say it won't be in this fashion where we add these first two and then second two and so on. It'll be a different kind of addition where we are taking, say, if we have, if TID 0 is what we are talking about and we have 8 elements, what we do is if it's less than 4, so we'll take the first 4 elements, only then we'll be making an update. So if it's the 0th element, then what we do is we add it to the TID plus 4, which will be 4th element. So 0 and 4, I mean, 0th element and the 4th element will be added. 8th and then, I mean, first and 5th will be added. Second and 6th will be added. Third and 7th will be added. So that's also kind of it's the same operation. It's just that we are not taking the adjacent elements. Rather, we are still doing the same thing, and we are doing those operations in parallel. And then we have a sync thread, so that again, we're assuming that all the threads, we are launching only one thread block or work group. We can, if we are using more than that, then we'll probably be needing a global barrier. We can use grid.sync. Yeah. So in the next step, size will be reduced to 2, and again the same thing will happen. Whereas so the result will be stored in that specific. So we'll keep doing the same thing, and finally we'll get the output. And we have this single variable to store the output value, and this the input of 0 will contain the final sum of all the elements in the input, and that update will be made by only the thread with ID 0. And because we have the sync threads here, we're making sure that all the operations, all the additions are completed before we move on to the next one. Now, prefix sum is another. It's a popularly used kind of an operation computation, whereas that so prefix sum of an array is a second array which contains so the element of the resultant the element at each index of the resultant array would be the sum of all the elements in the original array till that point. So like if you see this equation, so if we have an output array B, so B of I will be the sum of all the elements from A of 0 to A of I. So let's see if I have an example. So in this let's take this array like 4839175 So the result of this will be the prefix sum of this will be a resultant array which contains the first element as 4, the second element will be 4 plus 8, and the third element will be 4 plus 8 plus 3, and so on. And so the last element of the prefix sum array will be the sum of all the elements. So this is used extensively in a lot of places where like when we have a work list implementation, or we need to know how much space or how much space is required for a specific thread in an array, or things like that. We'll be needing this prefix sum implementation. So you can check this prefix sum implementation as well. It's also similar to the previous one, except that we'll be using one temporary variable here, and then we'll be adding it. So this will also be a login step process, but again, since we are exploiting parallelism, it'll be much more better. So I'll add a image which actually shows the exact additions which happen in this prefix sum implementation, but like before I upload it. So finally, when we come to the topics, before going into the next topic, we'll talk about synchronization between host and device functions. Host and device, not the host and device functions. So if like say we don't want, so we're trying to get maximum parallelism as our maximum utilization of our resources as much as we can. So if let's say GPU is doing computation, and if CPU does not have any data dependency on the output of this GPU computation, then we can make the CPU do useful work rather than making it wait. But such kind of a case would require us to use synchronization between the host and device. We'll write a program which prints a sequence of numbers from 0 to 10, where CPU prints the even numbers and GPU prints the odd numbers. So actually, you guys can take like 2-3 minutes and come up with some ideas as to how to achieve this. Yeah, Milan.
So Matthew, when you say synchronization between the CPU and the GPU, you mean the CPU should be executing something when the kernels are executing?
Both of them will be simultaneously executing at the same time.
Okay, my understanding was that the kernel call that we typically make is a blocking call for the CPU.
No, kernel call will not be a blocking call unless you use CUDA device, HIP device synchronize.
Okay, so it will trigger the task or kernel on the.
And then it will move on to the CPU will move on to the next instruction. That is it is. So you guys can take like I think 2-3 minutes and then try to figure out if you can come up with a solution to this. You may not even need to write code. If that's more comfortable, you can. Written as a solution. If device synchronize after each loop, after the for loop. Okay. Okay, global kernel I equal to 1, 2, I plus equal to 2. Okay, so the kernel is launched with 5 threads. Kernel goes ahead. Okay. Okay, but wherein in this case, like if you launch the kernel, is it not possible that the 1, 2, 3, 4, 5 will be printed in order? Should be with the ready. As in, sorry, is it not possible that the kernel execute first? So 1, 3, 5, 7, 9 will be printed, and after that the CPU will print 0. Yeah, that's what. So the sequence should be there, 0 to 10. So the sequence from 0 to 10 in order. Yeah, correct. So okay, again, there was like when we were taught this course, we were actually there was a feedback given to the instructor asking why would we use CPU to print? Why would we even use this case where we are printing it using two different devices where we print it using CPU and GPU? So the idea is that we want to show that this is possible, and then we can replace this with any other computation that we want. Yeah. So any idea how to do this in order? Go through the arrays in batches to print the first number through kernel. Send using CPU. Yeah. So yeah, that is correct. We'll be requiring a copy operation. Sing at the end of each loop. Yeah. Each iteration of the loop, right?
Probably scripts.
Correct.
The script, I think the description is much more easier than the code. So
Sure. That's with 5 kernel launches, it would be straightforward, but with only one launch.
okay, so a quick input to I think the feedback that you mentioned previously, that why do we need to print? So there are applications where we use the CPU to do the forward pass when the GPU is doing the backward pass.
That's true. But printing even numbers and odd numbers.
Yeah. So theoretically, if somebody understood the concept,
Yeah, correct. That's
I
true.
think
That's the purpose of this.
that's a practical implementation of what
Correct.
we're doing.
That's true. Wherein is saying maybe we could use a global flag accessible to both the devices. By both devices, do you mean like host and device, GPU and CPU? Okay, so global functions will not be accessible to the host function. Uh, yeah, that's also fine. Like that, yeah, that is GPU kernel should be used to print odd numbers. And coming back to Viren, yeah, like we'll see the different kinds of functions, but global functions cannot be. It can be launched from the kernel, but we can't use that function on the host side. We'll see examples of that in the next slides in the next topic actually. Okay, so this is a simple implementation of how we do it. It's essentially that we have a kernel called print, which takes a global variable, and it just increments that value there, and it prints the incremented value. So what happens is in the do while loop we have another host variable as well, host counter called edge counter. So and let's assume we initialized it to 0. So first the printf will print 0, and then we are doing a mem copy of the edge counter value into D counter. Now this is just 5 kernel launches. Yeah, that is true. It's not an efficient algorithm. But yeah, we'll see another example where we don't have different kernel launches. Yeah, so this is the like a simpler solution to this, which is that we launch it 5 times. Um, okay, so that is what you meant by with 5 kernel launches. Okay, I was confused with that. I thought it was like 5 threads were launched. Okay, yeah, you're right. With 5 kernel launches, it will be pretty straightforward because we just have to copy it back and forth. So yeah, so we copy the original value of edge counter into D counter and then launch the kernel. Kernel increments the value and then uh, prints the value, and then again we copy the D counter value back into edge counter. That's the same thing again. So until we reach the value of 10. So this is one way to do it, and then this is an even more kind of complicated where we launch the kernel only once. But here in order to synchronize, we use busy mechanisms in both the CPU and GPU. So again, we have to use a volatile variable, and then we are using we can use a global variable as well, but I've used a unified memory variable because we can use the same variable. We don't have to do the whole copying back and forth. Copying back and forth, like we saw unified memory yesterday. It's just that the copying will be internally taken care of by the memory copy engine, if I'm not wrong. So counter will be a variable on the unified memory. We'll initializing it to 0, and then we first call the kernel. So the kernel goes ahead and goes into the kernel launches, and then inside the kernel we check if the current counter value is a even number. So if it is, then we just wait there, and then we go into the while loop, and we go to the in the host code. We check if the current counter value is an odd number, but currently it is 0. So that while loop breaks. So 0 is printed and counter value is incremented. And then again, if the host code runs, it will see that it is a odd number, so it will not proceed. Meanwhile, in the GPU side, the while loop will break and then proceed to the printing the counter value. So we'll just see this code in action. So we have print 2.6. Yeah. This is the implementation that we just saw. So we'll just try running it. Oh, sorry, sorry, wait a minute. Thank you for. Okay, I'll just. So this is the implementation that we just saw, the same implementation that I just explained. We'll just compile this. So it should work, and then we run. And we can see that we've printed it from 0 to 10. So yeah, this is a pretty simple, rather, rather well, not that fruitful of a solution when we come to printing these numbers, odd and even numbers on GP. But as long as you understand the idea, and you should know that this is a possibility where we have operations which can happen on the GPU and the CPU at the same time. So maybe there are workloads, or rather big workloads, where we can split the data into two parts. Let's say 20% of the data is handled by the CPU and 80% of it is handled by the GPU. Or situations like that, or like how Milan had mentioned earlier, where the forward pass is handled by the CPU, where the backward pass is handled by the GPU. Only thing is that we have to make sure that both of these are happening in parallel. If the GPU is executing very much quickly, much faster than the CPU operation, then the GPU might wait. So we try to reduce this waiting time as much as possible. So we give both the GPU and CPU some kind of a operation or computation which roughly takes the same amount of time. That would be more efficient. But yeah, so this is some one possibility that we have. That actually concludes synchronization. I had to actually rush through a few concepts, essentially reduction and prefix sum. I think I rushed through it a little bit. We should have taken it a little more slower, but because of the lack of time, I think we did not have an option. So with this, we come to an end to synchronization. We'll move on to the topic section, which is like different topics across HIP. Does anybody have any doubts in what we've seen so far? In synchronization, or I hope yesterday's doubts were cleared with respect to log and atomics. Okay, so we'll take a short break for 10 minutes, and we'll resume after 10 minutes. And within regarding that atomics in that wavefront, like if we are using atomic add, then all we'll get a value of 64. Like they'll atomically increment. So even if they are warp threads, then we'll have a atomic addition. So it won't be just one if you're using atomic. If you're not using atomic, then yeah, it may vary. Okay, I think I have to restart my PC. My camera is behaving a little weird. So I'll just restart and get back to you. Okay, so we'll move on to the HIP topics session today. Uh, so we'll see what HIPify is, and then we'll see what errors in HIP are and how to handle them. And we'll see a rather small introduction to functions in HIP. And we'll see raw thrust and then streams and debugging. But I'm not sure how much of streams and debugging I'll be able to cover today. Yeah. But when I upload the slides, I'll add as much as I can. We can go through the slides and yeah. So we'll start with Heapify. We actually saw Heapify, I think, in the first lecture. So Heapify is a program which can automatically convert your CUDA code into HIP code. So since HIP is platform agnostic, it can run on both the NVIDIA and AMD GPUs. This is a pretty useful tool for people who want to run uh, HIP code on AMD GPUs or NVIDIA GPUs, but who've written only CUDA so far. Or if you have a CUDA program which you want to run on an AMD GPU, this will be a pretty helpful, useful tool. So, like Heapify can convert a lot of CUDA construct to HIP, but it might not cover everything, especially newer CUDA features and very specific NVIDIA libraries. So yeah, the usage is pretty simple. I'll show an example of how to do it. So we use the heapify-perl filename.cu, and then we redirect it into filename.cc. So okay, so I'll show you an example. So I have this example of a CUDA program, which is essentially a simple reduction sum example that we saw earlier, but it is grid.sync. Screen is not visible, is it? Okay, let me check that. Oh, okay. Yeah, I'll switch to that. Wait, just a minute. Yeah. So this is a simple example of a CUDA code which does the reduction sum kernel which we did earlier. So here we'll be using the cooperative groups, which is the grid.sync construct which we saw, which is a global barrier. So again, we can see that these are the CUDA runtime.h, cooperative groups.h, and IOStream, which is a standard C++ library. And again, the constructs here are pretty much related to CUDA. We have CUDA malloc, CUDA memcopy, CUDA memcopy to host, and then CUDA free. So it's mostly more or less completely related to CUDA. And the highlight is that we have CUDA related header files is here as well. So what happens when we do Heapify on this Heapify example .cu? So .cu is the extension used for CUDA file, CUDA kernels. Sorry, CUDA code. That's one other thing that I have to mention is that HIP does not have a specific extension that we have to use. We can use CPP or CC or anything is fine. Anything should be fine. Not anything, but yeah, at least C++ extension should be fine. So CC is one such extension which I've been using so far. So when we run this, what happens is it just prints the output onto the terminal. So in the example, in the slides, I had written a redirection operation so that we can properly redirect this output which Heapify-perl gives into the .cc file. You can see that the cooperative groups header file has been converted to HIP/HIP cooperative groups, and HIP runtime has also been added. Not sure why they have added this HIP runtime. It's possible that they are expecting it to be a like if they were not sure that if it's a user-defined header file or if it's in the same directory. That is why I guess they would have done that. But anyway, this program will compile properly. So we can see that everything else, I guess, remains the same. This is all the same constructs here. But as for CUDA memcopy, it got converted to CUDA malloc. Hip memcopy to hip memcopy host to device. So yeah, and CUDA free to hip free. I'll just try. I'll redirect this into a different file, and then we'll compile this .cc file, and we can see that there are no errors in what in the conversion. But yeah, there are pros and cons of using this PP5 tool, which we'll see. So the benefit is that it simplifies the porting procedure. There is we don't need a lot of manual intervention. We don't have to write code from scratch. And Hibify does like it does check compatibility, and if there is non-translatable CUDA code, it will definitely inform us. Although I've not seen such a situation, uh, that's something that they guarantee. And then it helps in maintaining a single code base for multiple GPU platforms, because HIP is platform agnostic. And when it comes to limitations, there are complex. We may not be able to handle complex CUDA constructs, or like newer functions which may not be supported on HIP. So one such example is dynamic parallelism is something which is not supported on HIP as far as I know. I'm not sure about the recent events, but it was not supported. So you can't call a kernel within the kernel, within a kernel. So, but in CUDA, if you've tried it out, you can do that. So let's say if you have a kernel called A, and inside that kernel you can call A again with few number of threads and blocks. So there it's the in that case the thread block scheduling or block allocation and thread allocation is kind of a little different from how we normally do it. Of course, we need to properly test it even after we do PP5, because there might be some things which may be missed by even PP5 or even the compiler when we compile it. So we have to actually properly test it so that we are sure we getting the expected output. And sometimes, yeah, performance is one thing we might need to manually tune to get the better performance, because there are things which are different. Let's say in HIP we have a 64 bit, 64 thread wide SIMD execution case, whereas in CUDA it will be just 32. So we might have to take care of such intricate details. So yeah, that's something that we have to keep in mind. So if we are kind of doing some kind of a performance optimization based on wavefronts. So yeah, before moving along, does anybody have any doubts regarding HP5? So yeah, HP5 is kind of an important tool when it comes to HIP, because yeah, it lets you run. It can easily convert things, so there's not a lot of programming overhead. So things the problem with like we have, I think, like other languages like OpenCL, which runs on AMD GPUs, but the programming overhead when you have to convert it from CUDA to OpenCL might be a little more. I'm not sure if there are tools for converting a CUDA code to OpenCL, but there are. I think if you know the I think in the initial lecture I had spoken about SYCL, which is a programming language by Intel. So there is a tool to convert CUDA code to SYCL code. So there are program converters from one language to another. So I'm not sure if it exists for OpenCL, but yeah, it reduces the programming overhead. It's a huge benefit of a tool like this. So I'll share my slides again. Okay, so we move on to what is called as errors in HIP, which is essentially that almost all the APIs that we have seen so far, like let it be HIP memcopy or HIP malloc, all these actually return value, and this is something that indicates if we had an error or not. So, like I said, almost all the HIP APIs return an error code, and it's a enum type. If I'm not wrong, it will be a HIP error underscore t. So, if there is no error, then the return value will be HIP success. Otherwise, it will return an error code. So, I think HIP success is a has an enum value of 0, and a non-zero value will essentially indicate that there was an error. So, these are a few functions which we can use to deal with errors. So HIP get last error will it will return the error code, but it will clear the last error. So if you've seen an error before this, then that error will be cleared when we call this function. But we'll get this and we can print this out. And HIP peak last error will just it'll return, it will retrieve the last error, but it does not clear it. So we can call HIP. If we call HIP get last error multiple times, let's say we got an error, and we called HIP get last error 2 times. The first time it will return the error code. The second time it will that error will not be there because it would have cleared the last error. And HIP peak last error would even if we call it multiple times, it will just keep returning the same thing. Then we have HIP get error string, which would essentially return the error string corresponding to the error code. So if an operation was successful, then it will give I'll show you an example where we use this. This is a kind of a macro which we've written. I'll show you where this macro is used, but if you see this, it's a HIP check. It takes something inside. We call it a command, and then which would essentially be the return value of one of the HIP APIs. And then if it is not a HIP success, then we are printing it to the standard error console. So it'll call the HIP get error string status, and it'll print that value, and at the end it'll just abort. So I'll show you an example of using this HIP error constructs. Let's see. So this is the basic implementation of HIP error, where we'll be using the maybe show what how exactly HIP check works. So first, this is all normal initialization. First here we're trying to allocate some memory on the GPU, which is a negative number. So this should obviously throw an error, and that we have the correct location here. And then we are trying to intentionally copy more data than the allocated, and we expect to see a error there. And this is the correct version of that. And then we are cleaning up using HIP free. So we'll try and see if we are getting the errors. So we'll do HIP cc. Right? So yeah, as we expected, we got a segmentation fault. Let's see what the out.log has. So yeah, it reports out of memory at line 28. So that is what we actually had put in the HIP check function, error HIP reports, and the HIP like get error string returned out of memory. That is the error code that we got. That is the string version of the error code that we got. Now what we can do is we can actually try changing it. We'll comment out this wrong implementation here, and then try compiling. Let's see. Again, we got a 4 dump because we're trying to access more than more than the allocated amount of memory. So we'll see if that is the case. Sorry about that. Yeah, invalid argument because we tried to do at line 34. I think this is the same error. But yeah, you get the idea. It's pretty much we can use this hip check. Or this is a pretty useful idea. This using the return value is a pretty useful idea because sometimes you may not be aware of like if you are doing some heavy computation. Like it, this is one experience that I had while I was doing GPU programming, which is that I had we had some computation which I was doing using streams, and for some reason I after a certain point I was not getting the required output, so I was just I couldn't understand. So we keep this debug print. So those of you have yeah written code, you know that if something doesn't have work out, you just put debug prints here and there and try to see what's happening. So all these prints were happening. At that point, I was not familiar with Rock GDB either. So I was stuck at that point, and I think it took almost 2 days, and then my assignment got late. And that's when I actually figured out, okay, why couldn't I use hip error? And then I realized that I was creating a lot of streams, which was causing memory to get exhausted. And that moment, I figured it out. So it is a pretty useful scenario because when it comes to hip or even CUDA, you may not get like the proper error message at a specific instance. So for example, if you are dealing with let's say 3D blocks or 3D grids, the number of threads in the blocks should be less than 1024. So if you're dealing with 3 dimensions, the product of those three should be less than 1024. But that we may not always think about that. Like we may just keep 32, 32, 32 as the block dimension, and that will obviously go beyond 1024. We may not notice that all of a sudden, but that will essentially cause the kernel not to be launched. And sometimes, yeah, it'll be hard to figure out such problems. And if we access memory out of bounds, we may not get a segmentation fault, or if we try to use a host memory location on the device, it's possible that that location is pretty valid on the device as well. So we may keep on getting an output, but it's just that it won't be what we are expecting. So that is something that you have to keep in mind with respect to hip check. And that may not return an error code even. So this is a general observation that I made, that be very careful when yeah, writing GPU code. So let's see if there are any other examples that I wanted to show. Okay, there's an example on GDB. Okay, we'll get to that when we reach GDB. Okay, I'll present my slides again. So again, this is the same code which we saw just now. So there are, I think, almost more than 15, I think almost 15 to 30 different error codes that are possible with respect to different APIs. I've not listed them, but I'll try to add them before I upload this slides. And one thing about the slides is that I think I uploaded parts of different based on the different days content. I uploaded different parts of each of the slides. So I'll be removing those slides and I'll upload the single slide for each topic. Like for synchronization, I upload a single slide, and you can use that. So that will be a more updated version. Like I think I've corrected a few things in certain slides. I'll upload that. This is just for your reference. So we'll come to the functions part of HIP topics. Before we move on to functions, any doubts in errors or HIPify? Okay. So we have different kinds of functions which we deal with on when we come to HIP programming. So we have this qualifier called as device. These kind of functions will only be executed on the GPU, so they cannot be called from the host. So it is only callable from the device code, which means that you can call it from a GPU kernel, like a kernel code. That is anything that is we can call it from any definition that includes the qualifier global. Or if we have any other function which has the qualifier device, we can call this device function from that. So devices essentially device functions. Why do we need such kind of thing? Because essentially, like why do we use functions anywhere? Like if we have some computation which repeats or some very big piece of computation, we'd like to make it more what do you say abstract, or not abstract is the word, but we'll write if you want to, it will make the code cleaner if we have more functions involved. So that's why we use device functions, so that we can clean up the let's say GPU code. If your kernel is quite large and there are parts of that which you can extract out into a function, then that would be really helpful for anybody who reads the code. So these are device functions. Then we have what we've been seeing as kernels, which is global functions. So global functions are executed on the GPU, but it is callable only from the host code. So the thing is that in CUDA, it is callable from both host and device, because kernels can launch kernels. But when it comes to HIP, that feature is not yet supported. But if and when that feature gets supported, we can say that global functions are callable from both host and then device. So kernels, obviously these functions are called using parameters, and this is how we define such a global function, which is a kernel, which is we have the global qualifier before the function, the normal function definition, and then we launch it using this special notation that we have, which is using angle brackets, where we define the threads, number of threads and blocks. So moving on to host functions. Host functions will essentially be normal function that we write, like any function that we've written before. I mean, other than HIP functions, which are executed only. It is executed on the host, and it is only callable from the host code. So usually we don't see host functions. Like that's a question as to why we need host functions. But usually they are along with host. We actually give. Okay, there's a typo here. Correct that. So along with host, we'll actually say that host device functions are we usually write. The dual functions is what we usually write. So then why do we just have a host construct? It's mostly for clarity, or let's say there are some CUDA APIs which can only be called from the host. Let's say memcopy is a function which is given by the HIP runtime. Sorry, about the CUDA runtime. So it is given by the CUDA HIP runtime. So, but it is only callable from the host, HIP memcopy or HIP malloc or HIP free. So these are things which can only be called from the host code. So this host qualifier will make it clear that okay, this specific piece of code is only callable from the host. And again, yeah, it makes it clearer to somebody who reads it. Okay, do not call this from the or if we accidentally call a host function on the device, then we'll get a compiler error. That will happen even if the host qualifier is not there. So here, I think this typo is here. It should be __ host __ device. So yeah, this would mean that this code is callable from both host and device. Yeah, so such kinds of functions, I don't think we have it inbuilt in the HIP API. But one thing that we have to make very sure when we do this dual functions is that if it takes some kind of a pointer, if you're passing some pointer to the dual function, we have to make sure that that pointer points to the correct memory location. Let's say if I'm calling this, let's say this function with memory location on the CPU RAM, then in that case, we have to make sure that this is called only from the host. If you call it from the device, I mean, there will not be any compiler error because this is a host device function, and it can be called from the GPU as well, from the device as well. But if you're passing normal DRAM, normal DRAM memory location into this function, yeah, we have to make sure that it doesn't access illegally or things like that. HIP malloc managed, we've seen one example of that. So those variables can be useful when we are dealing with dual functions because, yeah, again, we can be a little careless here. We can just pass the variable just like that. So that it's pretty useful when it comes to managed HIP malloc managed unified memory variables. So we don't have to consciously try to yeah, make sure that we're passing the proper value. Proper memory. Now, global variables on device. I think we've seen one example in logs. So underscore device underscore can be used to declare variables which are global too, which can be accessed from both kernels and device functions. So this is how we use it: underscore device underscore int global equal to 1. So if we have, even if you have multiple kernels, we can use the same variable name across. You don't even have to pass it as parameters. I think so far most of the examples we were passing it, and we've not seen examples which have multiple kernel launches. But yeah, across kernel launches also we can use such a construct. And now we'll come to rock thrust. So before that, any doubts in functions or I'll just check if I have a rock thrust exam. Okay, I think I have the slides. Okay. Okay, so what is rock thrust? Rock thrust is just a parallel algorithms library. So those of you are work with C++, you know what like STL library is. So it provides a bunch of different data structures or algorithms, like I think vector or vectors sets. Then we have sort, heap, make heap. All these kinds of different algorithms and data structures are provided in the STL library. Uh, so this is rock thrust is something similar to STL, but I don't think it is as extensive as STL. I don't think all the functions would be available. But it supports data structures like vectors and associated transforms. I'm not sure which other data structures will be available, but we'll be mostly dealing with vectors in my examples. We use C++ features like functors, and we'll see what functors are. So this rock thrust declarations are usually on the host, and we don't have to actually write kernel code in this case. So we'll just write the code on the host inside int main, and the thrust will take care of where the code will run. And yeah, that's a pretty that's very useful. So as we see examples, it will get a little more clearer. So this is one example of sorry. This is one example of using thrust. So yes, we have to include these special header files called thrust host vector and thrust device vector. So as the name suggests, host vector will be a vector on the host, and you can see that we are because we are using templates to make sure that all kinds of data types are allowed on the host vector. So here I'm creating a vector of integer vector of size 5 initialized to value 0. All 5 will be initialized to 0. So this will be a host vector. So any operation I do on this will be done on the host. So this is a dot size function which returns the size, which will be 5 in this case. And then again we are doing a pushback of 25, so we are pushing the value 25 onto that. So now if you check the size, it will be 6, because we have 5 numbers 00000, which was initialized initially, and then we pushed a 25 onto that. So now the size will be 6. Now what we have something called as a device vector. Again, it's the same syntax as host vector. The only thing is that uh, whatever allocation and deallocation happens, it happens. Which is taken care by thrust, will happen on the device. So as soon as you do d vector equal to post vector, and this is a valid operation. So as long as you do d vector is equal to post vector, the required so underlying, I'm assuming a kernel will be launched with the size of host vector. First we'll malloc certain amount of memory for d vector, and then initiate a memcopy operation to copy the data from h vector to d vector. So that is something that is possibly being done underneath. Although I'm not exactly sure about the implementation, but we can assume that it's like this. And if we try printing this, then we can see that it will be what we did in h vector. So, but this d vector again is allocated on the GPU and not on CPU. So these are some other functions which we have, which we use thrust for. So again, we have these different header files for each of them. This will be initializing a device vector of size 10 and initialize to 1. So thrust fill is essentially used to fill the given range with a specific value. So if you see this example here, a d dot begin actually gives the pointer to the first element. It's an iterator, if I'm not wrong. It's called an iterator, not a pointer to be, but we can think of it as a pointer. And d dot begin plus 7 will essentially go to the 7th element. So between this interval, it will fill the elements, the value 9. So initially it was 1, so now the first 7 will be 9, and then the remaining will be 1s. And this is another way how we can initialize a host or device vector, which is that as a constructor argument, we pass the starting of another vector and the number of elements that we want to copy. So this pointer plus 5. So whatever is in this range will be copied into the host vector. So host vector will only contain 5 elements, and it will be those elements which are in the first 5 elements of D. And so instead of this D, it can be another host vector as well. That is also possible. Now there is another function called as sequence, which essentially fills the elements of H with numbers from 0 to 1, 0 to whatever value it is. So if it is, but that depends on the size of the host vector, till what point you increment the sequence. So if it's a 10, if the size of H is 10, then it will fill the elements of H from 0 to 9. And yes, we have another copy function, which is essentially used to copy. In this case, it will be copying everything from h dot begin to h dot end. So we can actually do copy h dot begin to maybe h dot begin plus 5 or end minus 5 to this, starting from this address, which will be d dot begin. And sorry. And printing D is also straightforward. We don't have to deal with copying values from the host or from the device to memory and then printing it. We can use the standard cout construct here rather than using printf. If you remember, if we had to print on the GPU, we had to use the printf construct, which is, it is not actually bad way, but we have a cout which is usually much more easier to deal with than calling all that qualifiers and stuff like that. So yeah, this is another example of thrust. Does anybody have any doubts in thrust so far? It's a pretty useful library when we deal with HIP. There is a CUDA equivalent, and they just call it thrust. In HIP, we call it rock thrust, Rockham thrust. Yeah. There are a lot more functions which I've not included because it's quite a lot. So these are some other functions which we can use, which is find is used to find uh, all the values. I mean a certain value, and we give the iterator to the data structure, for the range in which we want to check, and then we give the value that we want to check for. And find if is a predicate value which is some kind of a condition. Let's say if if some condition is satisfied, all those cases will be printed by find if. Copy, as we saw earlier, it will be used to copy from one data structure to another. We saw the example of copying from vector device host vector to device vector. Then you have count, which will return the count of a specific value between the first and last iterators. Merge is another thing which we can use to merge to data structure. So we'll have the iterator to the first data structure, the iterator to the end of the first data structure, and iterators to the front and last of the second data structure. And then we'll have to use a result vector as well, which will have proper size to accommodate both the first and last for both the sum of both the sizes of both the arrays should be available in the result. Then we have sort, which is a normal sort function function call, and then we have sort, which uses a comparator. So if we this will I think by default it will sort in increasing order. So if we want to do it in decreasing order, we'll have to use a comparator object, or we can actually write a functor as well if we want some kind of a special sorting mechanism. Let's say if you want to say if we have a pair of coins, like we have an array of pair of coins, which has and when I say pair, I'm not talking about the standard pair. Like let's say we have a structure which contains pair, because I'm not sure if SVD pair is supported by thrust on device, but say we have a structure called pair which contains two elements, and if say x and y, and if the x element is same for 2 points, then we make sure that let's assume our requirement is that in such a case the element with a greater y is what comes as the first element in the result. In such a case, we can use this functor parameter. Or I think for decrease in like for sorting in decreasing order, then I think there is an inbuilt construct called, I think, thrust decrease or something like that is there. I'm not sure. I'll have to check that. So we have user-defined functions. I think I need user-defined functions. I think I have to correct this. There is some kind of rendering issue here. So we can define user-defined functions for thrust data structures using the transform function. So I think it is a little unclear as to what is happening here. So transform essentially takes five parameters. First being the if you're dealing with if you're dealing with the binary operation, binary transformation, then we'll have x dot begin, x dot end, and y dot begin. Where y dot begin is the beginning of the start of the. So we need when we're talking with binary operations, we need two operands, right? So x dot begin and x will contain one of the operands, and y will contain the rest of the operands. So we saw with vector addition. So each element will be added with each other, and the result will be stored somewhere. So it's the same thing here. So the operands will come from one array, from two arrays, and we have the operation will be defined by this function. So this is a functor. I'll show an example of Saxby. So and result.begin is also given. This can actually be y itself, but right now we are just giving it as result.begin. And this is SAXP operation. So SAXP stands for, I believe, single precision AX plus Y. So yeah, it's a quite common mathematical operation. So in order to use this functor, we define a structure called SAXP. It contains a constant value underscore a. So this is used to store the constant coefficient, which is like we have ax plus b, right? So that a is a constant. So that we'll store as a constant public member as it's not a public member because of the structure, but as a field variable inside the structure, and the constructor will essentially set the value of underscore a as whatever value we are passing to the constructor of SAXP. So this is how we set constant. Like if we have a constant variable, we have to set it within the constructor itself if it's not initialized originally. So this is how C++ asks us to initialize. So it's a special kind of a initialization. Those of you are from Java, I think you don't have to worry about this. You can actually call it within this brace itself, within the constructor brace itself. But in C++, they follow this different construct. And of course, we have to make this because it's a binary operation. We are overloading the parenthesis, and we are giving it two different parameters. And inside that, it will compute underscore a into x plus y. So that's all. This operation will essentially take two values and then compute x plus y. Then here we are just initializing a device vector, and then so transform we are calling it. So SAXP we are calling it with the parameter with the coefficient, constant coefficient. So underline inside this thrust will take care of doing this parallelly. So it will parallelly compute for each element and then store it in result. So we'll start with streams. I've not completely covered streams. So I'll just give a brief idea of what streams are. So streams are essentially used for asynchronous processing. So far we've only seen one stream, which is that the default queue or default stream which we've seen, where if we launch multiple kernels, all of them go into the same queue. That is a default queue. So streams are essentially queues which contain tasks which can be run in parallel. So if we have two streams and both the streams have different tasks, these tasks can run in parallel. So kernels we've seen so far, we've just launched them into the default queue. So there was no overlap between if we launch 5 kernels, all those 5 would go into the same queue, and they'll execute one after the other. Sorry, just a minute. So, so there was a definite ordering amongst the kernels that the kernel launches that we've seen so far. So you're pretty sure if we launch kernel 1, 2, 3, 4, and 5 into a stream, into the default stream, that order would be maintained. So this is an example of how to use streams. Suppose we have two kernels, kernel 1 and kernel 2. So we create a stream object, then we create the stream using stream create, and we specify the stream into which we want to launch it as the 4th parameter in the launch configuration. And so what happens is kernel 1 and kernel 2 can happen simultaneously. Whereas in the earlier case, 1 would definitely happen and then only 2 will happen. So yeah, that is something that we need to keep in mind. So within a stream, like if you're launching multiple kernels into a stream, then the relative ordering between them will always be the same. But when it comes to say cross streams, we have two streams, then the ordering amongst them will not be guaranteed. So that is something that we have to keep in mind. There are other stream constructs and such, but I think we are already running out of time. So we had a few things to inform, which is that one thing is that that mistake regarding the wavefronts, I inform it in the group as well. So HDS applies to HDS applies to both the streams. HDS will be between device and host. So if you're launching into two threads and then you have a HIP device, then the device will block it. I mean, host will block it, HIP device synchronize, but these will run in parallel. So is that clear, Viren? Yeah. So there is another thing called as HIP stream synchronize, which is used to synchronize between streams. And if you there is something called as HIP events as well, which also we couldn't cover, which was used to coordinate between streams. So I'll see if I can add those slides. Slides to this. Yeah. So like I said, the wavefront mistake I'll inform in the groups so that everybody gets this thing. And one thing is that there are other topics which in HIP, essentially with rock thrust, you can actually see a lot more things in rock thrust. That is something that you can explore. Then we have streams which can be explored in much more depth if you want to extract more parallelism. Then there was HIP memcopy async also, that also comes into the topic of streams. Then ROC GDB, which is ROC GDB, is something that you can use to debug your code. Like I had an example, but I couldn't properly get it to work, so I skipped that. So essentially, if you have you can see what all threads are running or which all kernels are running right now, or which all threads are running for this specific kernel. All that, it's a pretty powerful tool, ROC GDB. That is something that you can look into. And there are a lot of there is something called device to device communication. So if you have in a multi GPU setup, you can actually have a copy data between the devices, and there are such kinds of fancier things which you can do. There you can set a specific device to do a specific operation. There are a lot more topics that you can look into. So what I would suggest is that if you are going more into this HIP, then obviously you can check the ROCm API references there, and then you have the thrust. ROCm thrust also has a pretty extensive documentation. But as far as I could find the HIP normal runtime, normal APIs, there is not a lot of documentation related to that. It is there. I'm not sure. I mean, if it is there, I couldn't find it. Like compared to the CUDA programming manual, which is pretty extensive and it's quite detailed. Compared to that, for HIP, it is not that extensive. But obviously, you can refer to the CUDA programming manual to see what specific functions will do. But make sure that that is available to HIP as well. So that is something that you have to keep in mind. And so regarding my slides so far, like I said, I'll upload all the updated slides. I'll be removing the partial slides which I've uploaded so far, and I'll upload the complete slides. So for HIP topics, I'll need a little more time because I'll add few more things which you can refer to. So probably by today or tomorrow I'll upload it. And I think there was a query regarding videos were not uploaded. I think yesterday's and day before yesterday's videos have been uploaded, I think yesterday night. As for my references for my slides, so the flow of let's say the topics from computation, synchronization, memory, all that, I followed Professor Rupesh's structure of teaching, which is that, and a lot of things were actually taken from his slides. So he teaches GPU programming. He teaches CUDA. Last semester I had it. So most of the content, or like the outline of the content, was taken from his lectures. And a few of the things where there is a YouTube video, I think 30-minute video, or I think half an hour, 45-minute video from AMD regarding ROCm, how to use HIP. So it's a pretty simple and very concise uh, video. I think 4, 5, 6 videos are there. A concise video about how to use HIP and different HIP APIs. So those slides are also available online. You can check that out. And of course, there were certain things which I had used ChatGPT's help for. So some slides, and I think a lot of help regarding the preparation of the slides. The slides were prepared in LaTeX, so that was also yeah. And then coming to yeah, so we'll conclude this lecture. Does anybody have any doubts in any thing so far? Okay, so if not, yeah, as we conclude this, I'll actually like to thank each and every one of you for attending this lecture for this whole week. And yeah, it was a great experience for me, and I hope it was the same for you. This is actually, I think, the first time that I'm teaching such a big course, such a long course. Yeah, but it was a fun experience. I actually learned a lot from you guys as well. Your doubts, actually, I think, yeah, were pretty insightful. So yeah, we did fall out a little. We fell a little behind on schedule, but I think at least whatever I covered, I could cover properly. So, and like, of course, I'd like to thank NSM and both Professor Rupesh for giving me this opportunity. And yeah, once again, thank you all. And if you have any doubts, or if you want to get in touch, you can obviously email me. I'm in the NSM HIP group. You can post your doubts in the group if you have any doubts whatsoever. And So I hope this session was help you to write safer, more concurrent code for NVIDIA and AMD GPUs. So yeah, thank you all. I'll close this lecture now, and take care. Keep in touch. So if anybody has any doubts, I can stay back for a few minutes. If not, you guys can leave. Okay, I'll close this recording and then end this call.